Good afternoon, friends, and welcome back to the online learning platform at Department of Civil Engineering. I'm Rajesh Gopinath, and we are together for the course on environmental studies, which is part of public health engineering. If you can recollect, in the previous session, we had discussed about acid rain, which is a form of environmental pollution, or you might be more specific in saying it as air pollution, which, however, would have its impact on the various components of environment. Continuing the same trend, today we shall discuss about smog, the types of smog. Basically, in this presentation, I'll introduce you to the role of climate when it comes to magnifying the impact of pollution. Okay, of course, we shall briefly understand the classification, that is coal-induced smog and photochemical smog, and then we shall identify the various causes, understand the formation, okay, have a brief glimpse of the impacts and control measures for each of these type of smogs. Then I shall summarize the presentation and list the references for your kind perusal. Friends, whenever we speak about air pollution or environmental pollution, even if you talk about episodes such as Bhopal gas tragedy or the recent Vizag gas tragedy, okay, or probably even your Chernobyl disaster, if you go one step ahead and try to understand more details about those accidents or incidents, you will get to know that climate has played a vital role in magnifying the impact of air pollution. So what I'm trying to tell you here is, just like pollution can influence climate, climate can also influence pollution. Okay. Now, friends, in this particular presentation, I would like to tell you why London smog or Los Angeles smog is more fatal than it should have been. And to understand, we should have a brief idea of atmospheric stability. Friends, if you look at the present screen on your slide, okay, you can see something here as normal situation, and you can see a different situation which is called temperature inversion. Let's have the same visualization here and here. When I say normal conditions or normal situation, in simple word, it means that whenever there is any pollution taking place, it is able to escape into the upper atmosphere. Therefore, all the pollution gets dispersed and gets moved away. But if in case there is a circumstance wherein the pollution which is coming from probably your industries or your automobiles, okay, if it is not allowed to escape into the upper atmosphere, if it is forced to come back to the ground level, okay, that is when the intensity of pollution increases because the concentration of pollutants gets magnified. In technical terms, we consider this situation as an unstable atmosphere, and we consider this situation as a stable, stagnant atmosphere. Okay, let's try to have a better understanding of this in the next slide. Friends, if in case you have a circumstance or a climatic condition wherein the pollution is not being allowed to escape into the upper atmosphere, then it is most probably because there is a situation which has happened, which is called as inversion. Inversion can be of various types. We shall understand the same in the video later. But what I would like to tell you is, whenever disasters have taken place, say for instance, Bhopal gas tragedy, or for instance, London smog, which I would discuss today, okay, they've all taken place in the presence of a particular kind of inversion. And it is this inversion which made the disaster more dangerous than it should have been. So let us have a glimpse of this video to enhance your understanding before we actually get into the concept for today. Basically, what we have learned is as we go up higher in the atmosphere, temperature tends to decline. We have also understood that when we talk about our atmosphere, there are different layers: troposphere, stratosphere, mesosphere, ionosphere, thermosphere, exosphere. Okay, now what we need to understand is, since we are talking about environmental pollution, since we're talking about climate driven pollution, you need to understand that all of these are doctored or controlled due to the climatic activities which is taking place in troposphere itself. Usually in a daytime, what do you observe? You observe that the air around you is warm, and as you go upper, it would be cold. The transpose of this would be existing during the night. That is, the air around you would be colder, and as you go up, the air would be warmer. And we know very well that due to the differential density, okay, the cold air tends to settle down and the warm air tends to rise. Please observe this video very carefully. It speaks about how an inversion is created, how pollution is not allowed to escape during an inversion. Friends, now have a look at this. The smoke which is coming from your industries, basically these chimneys are technically called as stacks, and the smoke what you see is called as plume. So friends, if you do not allow this smoke which is originating to go into the upper atmosphere, then all the smoke would tend to come down. It would tend to come down to the ground level itself. So had there been a warm layer of air, then all the smoke would have risen up. But if you have a cold packet of air, then this smoke will not be able to rise. Basically, this is what happens during an inversion. See, that smoke is not being allowed to go up in the upper atmosphere. Had that happened, then the pollution would have diminished. So let me give you some more information with respect to inversion. Typically, these types of inversion have their own variable attributes. For instance, at what time of the day they occur, how long do they occur for, during which season it happens. Okay, for instance, your radiation inversion is most often during winter, your subsidence inversion is most often during summer. Radiation inversion is something which happens during the night time, and it breaks, okay, the moment your sunrise happens, and it can go hardly for few hours. But subsidence inversion is something which can continue for several days and can go on for months together. Radiation inversion is something which happens very close to the Earth's surface, while subsidence inversion takes place at great heights. All right, so now let's try to understand with respect to the dispersion of the smoke which originates from the industries. Friends, what we need to understand here is there are different patterns by which the smoke comes out from the industries. Okay, now how the smoke arises and what pattern it takes entirely depends on the climatic conditions. Is there an inversion which is existing? Is there a wind? How fast is the wind? In which direction the wind is moving? So typically what I'm trying to stress here is climate plays a very important role in how pollution is enhanced. So with this brief introduction to a requisite with respect to today's presentation, now let's try to proceed further. Friends, basically, whenever we speak about environmental pollution or air pollution, it's not something new. The accounts of pollution of your urban air, it goes way back into, let's say, ancient Greece, ancient Rome. In fact, during your medieval times, the burning of coal has led to high concentration of pollutants. So friends, when we speak about pollution, we know very well that, as you can see on the screen, there are two types of pollutants: primary pollutants and secondary pollutants. Primary pollutants are those which are directly produced due to the activity. Say, for example, burning of coal, or let's say a volcanic eruption. Secondary pollutants are those which are formed due to the reaction between two or more primary pollutants. Now, when we say smog, smog is nothing else but smoke plus fog. So smog is basically a secondary pollutant. Okay, in fact, the word smog was coined by a gentleman, a doctor, in the year 1905, named as Harold Antoine de Vieux. Okay, now friends, now when you speak about smog, there are various types. Okay, you've got the classical smog, you've got the modern smog. Okay, classical smog is also called as a coal-induced smog. Modern smog is also called as a photochemical smog. Classical smog is which we have, infamously always learned as London smog or reducing smog or sulfurous smog. While your modern smog is something which is, prominent in present day, which we also call as photochemical smog or oxidizing smog, or most infamously as Los Angeles smog. Friends, what we will understand today is all this pollution which is taking place. Okay, when we talk about the smog component, okay, now it can originate due to industrial activities, or it can originate from domestic activities, or it can originate from automobiles. But having said all this, when you say smog, we are still talking about a very high localized concentration of pollution in a stagnant, stable air. So what is this pollution you're talking about? It could be oxidizing agents or reducing agents, and fourth. Okay, now with this understanding, let us start with the first type of smog, which is your coal-induced smog. As I said you, it's also called as London smog, reducing smog. Okay, now typically, basically what happened is during your 19th century, or let's say early 20th century, during the Renaissance or the Industrial Revolution, okay, there was a lot of activities which was taking place in the name of development, which basically led the burning of coal. Now, coal typically contains carbon and contains sulfur. So obviously, when you burn coal, it produces carbon dioxide, carbon monoxide, sulfur dioxide, and sulfur trioxide. It all depends on the amount of air or oxygen which is available when the coal is being burnt. So what you need to primarily understand is when you say coal-induced smog, it is basically due to the burning of coal. And primarily why in London? Because it was the epicenter of industrial revolution. So friends, if in case during your winter time, as it is cold, okay, you wish to feel warm and then you start burning coal in your domestic hearths, or let us say even if you're burning coal in your kitchen, if you do not use the fuel wood, okay, these also would eventually become the causes, or let us say sources, for the burning of coal. And typically, as I told you, when you burn coal, okay, there would be production of sulfur dioxide and soot particles, which is typically your fine carbon particles. Friends, what exactly happens in your coal induced smog is there are series of reactions. As you can see on the screen here, okay, typically when you burn coal, there is production of sulfur dioxide or sulfur trioxide, which actually reacts with water vapor and becomes acids. Let's say sulfuric acid or sulfurous acid. Sulfurous acid invariably also gets oxidized and becomes sulfuric acid. Friends, you please need to understand that the reason why it is called as reducing smog is because there is production of acids in this type of smog. Okay, now let's go a step further. Please understand that coal induced smog can originate due to release of sulfur dioxide, which can come from thermal power plants which primarily burns coal. But sulfur dioxide can also be emitted if there is a forest fire. Sulfur dioxide can also be emitted if there's a volcanic eruption. So there are both natural and man-made sources for the release of SO2 and SO3. But you know very well that forest doesn't catch fire every day. Volcanoes do not erupt every day. So primarily, my friends, 90% of the sulfur dioxide which is coming into the atmosphere is due to man-made activities. Now, what would be the impact of having a coal-induced smog? Typically, since you're talking about fine carbon particles, the smog would have an appearance which is blackish, and since it also contains sulfur, it would also be slightly yellowish. Typically, it would be a grayish appearance. And since you're talking about acids, and friends, since you're talking about the king of chemicals, since you're talking about sulfuric acid, the pH would automatically go down well below 2. Okay, and since you're talking about fog, okay, you know very well that fog is nothing but dispersed water droplets. Typically, visibility is also impacted, okay, and invariably you would end up with several cardiovascular issues and respiratory diseases. For instance, since you're talking about carbon monoxide being produced, you know very well that when we inhale carbon monoxide, it reacts with carboxyhemoglobin. Okay, that is your hemoglobin, and becomes carboxyhemoglobin, which has a reduced oxygen carrying capacity. So that leads to cardiovascular issues. Similarly, if you inhale the air which contains these acidic aerosols, then you might also end up with diseases such as bronchitis, emphysema, pneumonia, and tuberculosis. Friends, so to a quick recap, what are the primary pollutants when it comes to your coal-induced smog? It is sulfur dioxide. What is the secondary pollutant when it comes to your coal-induced smog? It is sulfuric acid. Please remember, we cannot control climate. We cannot control sunlight. We cannot control water cycle. We cannot control formation of water vapor or oxygen. In other words, there is no way that we can control the formation of sulfuric acid. But what we can do is we can control the production of sulfur dioxide, which is a primary pollutant. Hence, all the control measures must be targeted in restraining the release of sulfur dioxide. Okay, let's try to understand much about this with the case study of the Great London Smog. Friends, London smogs were highly infamous in the 19th and early 20th century because they used to get formed every autumn and winter, and mostly due to the sulfur emissions which was coming from the domestic fires and the coal burning industries, as I told you, due to the great industrial revolution. Several episodes of London smog have taken place within a decade. But what happened between 4th to the 10th of December 1952 was the most shaking episode, because during that day, okay, during those series of days, the disaster was at its peak. And you had smoke which is coming out, which was yellowish and blackish in color. Sulfur dioxide levels had gone as high as 4,000 milligrams per meter cube. The pH had literally fallen down to 1.4. Visibility was so poor that for at least 48 hours, or let's say 2 days, you could not see beyond 10 meters, sometimes 50 meters. If you wore a white shirt, it hardly took 25 minutes for that shirt to turn black. Okay, if you kept your hand in front of you, sometimes even you could not see your hand. So that is how dangerous the Great London Smog was. Okay, now as an outcome, what basically happened is, in the year 1956, United Kingdom introduced what is called as the Clean Air Act. Okay, this act was directed at the domestic sources of smoke pollution. Now, but despite that, there were still episodes of smog which is continuing. And finally, in the year 1968, they came up with what is called as the Clean Air Act, which also brought the tall chimneys into consideration. So basically what was happening here is these acts were introduced to ensure that we had good practices, okay, when it comes to burning coal. For instance, coal comes in various varieties. Now the coals which are inferior, let us say peat and lignite, they contain more of sulfur and carbon. Okay, so let's try to understand much about the London smog and how it led to new revelations in this video.
Hello and welcome to History Pod. On the 5th of December 1952, the Great Smog of London descended on the British capital due to a combination of air pollution and weather conditions. To maximise revenues in the aftermath of the Second World War, the British government had opted to export the country's better quality hard coal and retain the more sulphurous low-grade coal for domestic consumption. Smoke from burning this coal in domestic fires to offset the particularly cold winter of 1952, combined with pollutants from Greater London's numerous power stations, factories and public transport, to create a thick, noxious blanket of smog over the city. The thick, yellow-black smog was held over London for more than 4 days due to the arrival of a high-pressure weather system.
This is what you need to understand, the high-pressure system, which actually resulted in ensuring that those sulfur emissions are not escaping into the upper atmosphere.
This caused an anticyclone that stopped the polluted air from rising into the atmosphere. Windless conditions and London's position in a river valley also meant that the smog was unable to be blown away. Visibility in the city was reduced to just a few meters, bringing public transport to a halt and forcing schools and businesses to close. Meanwhile, people across the city breathed in the toxic air and began to succumb to respiratory infections.
Friends, what we need to understand here is, when we say respiratory diseases, these diseases alone accounted for 59% of increase in the deaths which was registered in the week. Okay, and I'm talking about the week which ended in, let's say, 13th of December. Okay, in fact, it went on to rise to 76%. In fact, when you look at the deaths of 4,000 to 6,000 people, only 2/3 of the victims were over the age of 65. In fact, the death rate during this period actually rose, most, between 45 to 64-year-old people.
Cattle at the Smithfield show at Earl's Court reportedly suffocated, and while nobody made the connection until several months after the smog had lifted, estimates state that between 4,000 and 12,000 Londoners died as a direct result of breathing the polluted air. In response, the government began to rethink its policy towards air pollution, and in 1956 introduced the Clean Air Act that established smoke control areas where only clean fuels could be burned, precipitating a shift towards the use of cleaner coals, electricity and gas.
Basically, what happened is, as I told you, the 1956 Clean Air Act was actually directed at the domestic sources of smoke pollution. This resulted in, the local councils in setting up smokeless zones and making also grants to the householders to convert their houses from traditional coal fire to heaters which were fueled by gas or oil or smokeless coal or electricity. So what we need to understand is 1956 basically targeted the domestic fires
as sources of heat.
So why we need to understand, why we need to go back to the past is because, if we tend to forget the past, we are condemned to repeat it. Okay. Unfortunately, despite these lessons which we learned in 56, 52, okay, and we went on to 68, unfortunately, the smog of 1991 has clearly demonstrated that efforts that we are doing is probably insufficient, and we need to continue. We need to improvise to counter the air pollution, because we are talking about the future generation. So friends, this was the session with respect to your coal induced smog, which is infamously called as the London smog. Now let us move on to the next part of today's presentation, and that is your photochemical smog, also called as oxidizing smog, okay, or your infamously the Los Angeles smog. Unlike your London smog, which is grayish or blackish in color, this smog is primarily brownish in color. Friends, the very reason that you called London smog as coal induced smog is because we used to burn coal. But the reason why we call photochemical smog as so is because we are talking about reactions which are taking place in the presence of sunlight. We are talking about photolytic products. We are talking about chemicals, okay, which are being produced due to the reaction in the presence of sunlight itself. Unlike your London smog or coal induced smog, which basically happened due to industrial pollution or pollution from the domestic fires, your photochemical smog is mostly due to automobile pollution. Okay. And the reason why we call it oxidizing smog is because there is production of chemicals which have an oxidizing ability. Friends, oxidizing smog is actually present in all modern cities, but it will be more prevalent or common in those cities which have a dry climate or sunny and warm climate. And especially if your city has a large number of motor vehicles, then yes, there are more chances of these kind of smogs occurring. Okay, now the photochemical smog was basically first described in the early 1950s. Probably 1947 was the first time when it was observed in Los Angeles. But it has been observed also in other places such as Tokyo, Mexico, Athens, Johannesburg, or the very own Beijing that you see on the screen here. Typically, when I say photochemical smog, we are talking about a noxious mixture. Okay, we're talking about a mixture of chemicals such as oxides of nitrogen, okay, the volatile organic compounds. Both of these are released from automobiles itself. Then yes, we are also talking about the ozone. Please remember, we are not talking about stratospheric ozone. We are talking about the tropospheric ozone, the ground level carcinogenic ozone. And yes, primarily we are going to speak about PAN, peroxyacetyl nitrate, or peroxyacyl nitrate. Friends, yes, there are primary pollutants and secondary pollutants involved in the formation of your photochemical smog. The primary pollutant is basically oxides of nitrogen, okay, which is coming from automobiles, and the unburned hydrocarbons, which is also coming from automobiles. Now you may ask me why. We know very well that your petrol driven vehicles or your diesel driven vehicles are actually running on a mixture of hydrocarbons. Your crude oil, your petroleum, is basically a mixture of hydrocarbons. And when your petrol or diesel burns due to incomplete combustion, due to inadequate oxidation, there is production of unburned hydrocarbons. Okay, now also that it is not just the fuel which is burning, it is a fuel plus air mixture which is burning. And you know very well that air contains more than 78% nitrogen. That is why when your fuel air mixture burns, you have production of oxides of nitrogen as well. So friends, that is your primary pollutants, oxides of nitrogen and unburned hydrocarbons which are coming from automobiles. Of course, if there are certain industries which are specifically releasing them, they also join the list. Now, when it comes to secondary pollutants, you typically have ozone. Okay, apart from ozone, we also have the formation of PAN, that is peroxyacetyl nitrate, or PBN, peroxybenzyl nitrate, or PFN, peroxyformyl nitrate. Of course, this end product typically depends on the number of carbon. Okay, now let's try to understand the formation of your photochemical smog. Let's have a look at the video first.
Nitric oxide and nitrogen dioxide can also react with the hydrocarbons instead of ozone to form other volatile.
So what he's telling here is, in the photochemical smog, the end product is actually PAN. And for that to happen, for that to form, you need oxides of nitrogen, you need oxygen, you need water vapor, you need sunlight, you also need unburnt hydrocarbons, and yes, if ozone is present, that also would result. Now let's try to understand the reactions.
Compounds known as PAN, that means peroxyacetyl nitrate, reactive hydrocarbon from the exhaust interact with ozone, two from the hydrocarbon-free radical.
So basically what happens is, when the unburnt hydrocarbons are released from your automobiles, they react with the ozone, which is there in the lower atmosphere, in producing a free radical.
This hydrocarbon-free radical rapidly reacts with oxygen 2 from another hydrocarbon-free radical. Then the free radical reacts with nitric oxide to produce nitrogen dioxide and the free radical hydrocarbon. This new free radical next interacts with oxygen to yield a stable aldehyde and hydroperoxyl radical. Hydroperoxyl radical, then reactive with another molecule of nitric oxide to do nitrogen dioxide and hydroxyl radical. The hydroperoxyl radical is extremely reactive and rapidly reacts with a stable hydrocarbon to yield water and regenerate the hydrocarbon-free radical, thereby completing cycle. The aldehyde may initiate another route by interaction with the hydroxyl radical, leading to the formation of an acyl radical, peroxyacetyl radical, and finally peroxyacetyl nitrate. Peroxyacetyl nitrate is also known as peroxyacyl nitrate.
So let's have a recap with respect to the formation. So friends, basically what is happening is, you find that there is formation of ozone and oxygen. You also find that the oxides of nitrogen is changing its state. You see nitric oxide, you see nitrogen dioxide. So typically what is happening is, ozone is releasing oxygen for triggering reactions. Okay, similarly, oxides of nitrogen is also doing the same function. They're also contributing oxygen for triggering the reactions. Finally, what happens is, due to these reactions, okay, your unburnt hydrocarbons eventually end up in forming aldehydes. Okay, and eventually the aldehydes, again with further subsequent reactions, results in the formation of the highly carcinogenic peroxyacetyl nitrate. So typically it's a vicious cycle, okay, which is magnified during the afternoons. Please understand, while your London smog was something which happened during the early morning hours, your Los Angeles smog or your photochemical smog, since it requires sunlight, is more stronger, more predominant and prominent during the mid-afternoon and in the summer seasons itself. Okay, while your Bhopal gas tragedy or your London smog were more prominent during the winter season, your Los Angeles smog or the modern smog is observed in the summer season itself. Okay, now what is the impact? Now, you know very well that when I spoke about London smog, the impact was because of the sulfur dioxide being released and the sulfuric acid being produced. Okay, similarly, the impact of photochemical smog is due to both the primary pollutants and secondary pollutants. But what the difference is, while London smog resulted in imminent, immediate deaths, Los Angeles smog would not kill you immediately, but would result in prolonged chronic exposure. Okay, you know very well that ozone causes respiratory issues, can cause damage to plants, it's a carcinogen in itself. Okay, it is bad for the eyes. Similarly, peroxyacyl nitrate is also eye irritant, respiratory issue. Okay, it can cause skin cancer and again damage the vegetations. So friends, the impact of the smog is due to both the primary pollutants and the secondary pollutants. And of course, if you need to control it, you need to again understand that we cannot control the secondary pollutant. So you need to focus on controlling the primary pollutant. In fact, you know, since the recognition or discovery of Los Angeles smog in 1947, various innovative and creative ideas have been released by engineers and inventors, you know, to get rid of this smog. Okay, somebody suggested that, you know, one way was to connect all the Los Angeles industries to a massive network of exhaust pipes. But we should understand that the problem here is with respect to automobile emissions. Somebody even said that, you know, let us go ahead and cut holes in the mountains and install huge exhaust fans, which can, you know, suck away all the smoke which is being produced. Of course, economically it's not feasible, and ecologically it's a disaster in making. Somebody even spoke about, you know, blackening the whole section of the eastern mountains of Los Angeles, so that, you know, we will be able to store the heat and create thermal currents. Okay, therefore, as an outcome, the westerly winds would blow the smog over the mountains. Unfortunately, all these ideas would not work out, and eventually United States of America introduced what is called as the Clean Air Act in 1970, and they constantly amended it repeatedly until 1990. Friends, I'll just give you a small glimpse of what is Los Angeles smog. Now, typically when we speak about Los Angeles smog, it is highly, you know, developed, modernized and urbanized area, which has high, you know, numbers of motor vehicles. Now, what we need to understand is Los Angeles is located in a valley. Okay, it is surrounded by a mountain. So typically what happens is when there is any smoke which is produced by these industries or automobiles, they need to escape in the upper atmosphere. But when the Los Angeles smog had happened, typically there was an inversion which had happened over Los Angeles, an inversion which did not allow the smoke from escaping. And the very fact that you have a mountain, okay, which is blocking the circulation of air or ventilation, made things worse. So eventually what happens, you have this, you know, the smoke which is circulating constantly in your own locality, okay, causing a lot of damages and health issues, finally until it is blown away. So friends, what I'm trying to stress here is, you know, sometimes climate can be cruel. Okay, but we need to understand that this cruelty is not because of the geographical location or the climate itself. It is because of the human intervention. It is because of the anthropogenic sources. Okay, even if you're looking at the case study of Delhi, New Delhi, okay, now New Delhi is suffering a lot in this winter season, and it's because of the fires, okay, stubble burning, which is happening in the neighboring states of Haryana and Punjab. But the climate of Delhi does not allow that smoke to escape, and it is the people of Delhi who are suffering. Okay, so friends, to summarize the London smog and Los Angeles smog, London smog is a classical smog which was recognized several centuries ago, while Los Angeles is a modern smog which has been observed since the mid 1940s onwards. Now, London smog has a grayish, blackish, yellowish appearance, while Los Angeles smog has a brownish appearance. London smog, also called as coal-induced smog, is a reducing smog, while Los Angeles smog is a photochemical smog and an oxidizing smog. London smog is observed during the early morning hours and there is presence of radiation inversion, but Los Angeles smog is observed during the peak mid-afternoon, okay, and becomes severe when there is subsidence inversion. Now, London smog, the primary pollutant is sulfur dioxide and carbon monoxide, but Los Angeles smog, it is unburnt hydrocarbons and oxides of nitrogen. The secondary pollutant for London smog is very well sulfuric acid, but when it comes to Los Angeles smog, it is ozone and peroxyacyl nitrate. Please remember, London smog episodes were more predominant, okay, and prominent during winter season when the temperature is very cool, when the days are foggy and humidity is very high. But Los Angeles smog has been more observed during summer season when the temperature is pretty high, okay, and the humidity is very low. So friends, what we need to understand is, we have several lessons taught in history by us with respect to London smog and Los Angeles smog. But have we learned our lesson from 1952 to 1991, okay, or from 2016, which is observed in China? We need to make sure that we do not repeat what has happened in the past, because this is a global disaster. It's a recipe in making which can wipe out huge number of people. So friends, these are the references for your kind perusal. Okay, please feel free to go through any material that can befit you in enhancing your knowledge. Friends, in the subsequent class, we shall discuss about environmental pollution and abatement, wherein we shall look at case studies and issues with respect to water pollution. For instance, the Minamata Bay disaster. So I thank you all for your patience. Thank you. If you got any doubts, please raise it.